Can you all hear me very well? We good? We good? Okay, well, as Liz so graciously pointed out, I am Dan Haden. I'm a graduate student here in the Department of Physics Astronomy. And let's talk a little bit about some non-traditional applications of lasers for Extreeeeme Light. But before I get into that, I want to start with a little bit about myself. See, I was born and raised here in Nebraska, specifically a small town about an hour to the west of Lincoln called Aurora. Now, Aurora has a unique scientific claim to fame for a famous scientist who generated this image. He was also raised there. And his name was Harold Doc Edgerton, and he developed a very fast shutter for cameras that allowed people to see very quick processes, such as this bullet traveling through this apple. Now, being raised in a community that embraced science like this really motivated me to become the scientist that I am today. But one thing's very funny about living in a small town. When you return home after being gone for a while, and you go somewhere like the grocery store, the bank, or Runza, you inevitably run into somebody that you know. And then, of course, you're stuck getting asked the dreaded question, well, what are you doing now? By now, I've developed a general spiel for these occasions, and it goes a little bit like this. Well, I'm working on my PhD at the University of Nebraska, and I work at the Extreeeeme Light lab, where I get to work with high-powered lasers. But as soon as I mention lasers, the proverbial light comes back to their eyes as they think through their traditional experiences with lasers. And generally, I try to head them off before they arrive at the typical response of, do you get to blow anything up? No, I definitely don't blow anything up. But I do get to produce light that is brighter than the surface of the sun. And we do this in the Extreeeeme Light lab with the laser system named Diocles. Note that I said system because it really is a bunch of lasers working together in harmony to produce some of the highest intensities of light here on Earth. But the key to producing such light boils down to three ingredients: energy, time, and area. The first of which I want to talk about is energy. And since I'm talking about Extreeeeme Light, you must be picturing that we pack a huge amount of energy into our laser. Well, typically we operate with about 5 joules of energy in our infrared beam. But to put that into perspective, if you would place a baseball in a catapult and launch it with that same amount of energy, it would only travel about 5 yards. Well then, what's the key for power, right? Well, the key for unlimited power, or petawatts of power in our case, is squeezing this energy into the shortest amount of time as possible, which ends up being about 30 femtoseconds. Now, 1 femtosecond is 10 to the minus 15 seconds. So if you would compare 1 femtosecond to 1 second, it's the same as comparing 1 second to the age of the universe. Now, while having this energy compressed in a short amount of time gives us very high peak power, it's nothing unless we focus it. And in our lab, we typically focus the beam down to a spot size with a diameter of about 10 micrometers, which is smaller than the width of Einstein's hair here. So when we utilize these 3 elements to create Extreeeeme Light, it does actually look reminiscent of that space station that's not a moon, as you can see here in this nice picture of one of our amplifiers. And instead of blowing up Alderaan, when we focus our laser, some exciting physical phenomena occur. Like in this case, where we focus a very weak beam from our laser into a beaker of water. In this picture, the infrared beam, which is invisible to your naked eye, it's coming from the right side here. When it enters the container, it begins to interact with the molecules by ripping electrons left and right. And due to this transfer of energy between the light and the material, you end up generating harmonics, which gives you all sorts of frequencies of light in a process called supercontinuum generation. And you can see that here in the form of this white light that's produced in the beaker. So, at this point, I've told all of you and my friends back home how grand and powerful this laser is. But the next question I'm usually faced with is, what is the purpose of all of this? What can you do with your laser? Well, some people may be inclined to strap our lasers to the heads of sharks. But let's examine the advantages and disadvantages of that. Yes, they're very quick to move in water. They definitely can be considered autonomous. And I'm sure it would take not much to maintain them. You just have to throw your minion into the water every once in a while, right? But for the disadvantages, first of all, PETA may not feel very comfortable with having lasers close to sharks' eyes, since laser safety goggles have not been developed for sharks. But more importantly for me is that this would only be good for annihilation and not for any reasonable science. So what then is reasonable science, you might ask? Well, our lab specializes in two very unique processes which can be utilized to understand and study the fundamental properties of nature. And the first one I want to tell you about is a process called laser Wakefield acceleration. So to describe laser Wakefield acceleration, let's first focus on this picture. And just to assure you guys, there are no sharks in the water up there, okay? Let's instead become proper scientists here and make some observations about this. In this picture, there's a bunch of water here, and there's also a boat traveling through it. And so that boat is creating waves behind it, which we call a wake. And then if we throw a wakeboarder into the wake behind the boat, he can then ride along the waves along the river without being directly attached to the boat. Now, a very similar thing happens when you focus a high-intensity laser pulse into a plasma. This image here is a simulation of such an event. We have the plasma, and we have the laser traveling through it. Behind the laser pulse, there's a wake structure, just like up here. And in that wake structure, we can trap electrons and accelerate them to very, very high speeds, and subsequently high energies. It is the utilization of this technique that we have been able to shrink the size of modern-day accelerators from something that is Memorial Stadium size to something that can fit in the palm of your hand. The other technique we specialize in is called Thomson scattering. Now, this technique piggybacks off of laser Wakefield acceleration, as we still must use a drive laser focusing into a plasma to produce high-energy electron beams. Once we have these electrons, we can then bring in a second laser pulse and focus it onto these electrons. When these electrons then experience an external electromagnetic field, well, they begin to oscillate, kind of like a little Oompa Loompa dance. And there's a simple law in physics that when you have an accelerating charge, it will radiate energy. And this comes off of these electrons in the form of X-ray radiation. These X-rays are then high energy, and since the laser was used to generate them, they also have a very short pulse duration. So after describing these two rather complicated techniques, it seems like running an experiment in our lab would be pretty badass, right, guys? Right, guys? So, of course, the next question I get asked is what an experiment is like in our lab. Well, for that, I'm going to turn to Sheldon, Leonard, Howard, Raj, and Penny to show you a true pop culture representation of what that is like. But first, let me put on my safety goggles.
Preparing to fire laser at the moon.
Make it so.
There it is. There's the spike.
2.5 seconds for the light to return. That's the moon. We hit the moon.
That's your big experiment? All that for a line on the screen?
All that for a line on the screen. Well, this is probably actually the most accurate representation I've seen for what life is like on an experimental day in our lab. See, we spend many months in preparation getting every little detail correct, and then on the experimental day, we align the laser, close our 1-foot-thick lead door to protect us from the ionizing radiation, and then we fire away. The only difference from this clip is not only do we get lines, we get numbers and pictures. But these lines and pictures are very special, and they can give us a variety of insights from real-world applications to clues about the fundamental rules of nature. Now, one real-world application that we've performed in our lab is an experiment where we sandwiched a uranium disk between two plates of steel. We were then able to form a radiographic image that lets us clearly identify that uranium was present. Now, this successfully demonstrated that we can use our special laser-driven X-ray source for homeland security purposes, like sniffing out weapons of mass destruction at the ports. Another technique that we can apply to our source is the ability to study ways to controllably excite and de-excite selective energy states of the nucleus in order to pave the way for nuclear batteries in the future. But one of the final applications of our source that I want to share with you and all my friends back home is an application that's an extension of Doc Edgerton's work. We can use our ultra-fast X-ray source to create pictures very similar to that of the apple and the bullet, but not of large-scale objects, but of molecular processes like this, which is a hydrocarbon ring unfolding into a linear structure in a matter of femtoseconds. So with that, I hope I've steered you away from the traditional ideas of what a laser can do and what it can be used for, and enlightened you on some of the many applications of extreme light.